Well, welcome. Welcome to the first of this industrial engineering live stream series. My name's Neil Ashton. I'm a distinguished engineer here at NVIDIA. And hopefully, if you're interested in AI physics, GPU accelerated solvers, digital twins, agentic AI, then hopefully the show and this series will be for you. This is going to be the first of hopefully many that we're going to go through and deep dive into topics that hopefully are interesting for you. This is not a webinar. This is not a one-way conversation. This is hopefully a two-way conversation at the very least. So please do write comments on however you're looking at this, whether it's on YouTube or LinkedIn or X or wherever else this is being streamed. And of course, you may be listening to this as a recording, and that's fine too. Maybe leave a comment, and maybe I'll try and take a look at the channel and every so often give some feedback or answer some questions that I see after the event. So yeah, what I'm going to try and start off with in today's, which is going to be about 20-25 minutes, so I'll try not to go on for too long, is really to set maybe the high level scene of, what are we doing at NVIDIA when it comes to industrial engineering, computational engineering, computer-aided engineering, computational fluid dynamics, however you want to split it. I'm going to try and give a bit of an overview, and that will set the scene then when in the following episodes, we're going to deep dive specifically in some of these areas. So today is to more go over the top. So Mark, if you could maybe show some of the slides that I have, I'm going to go through a couple of slides, and hopefully it sets the scene a little bit. So, one of the things I think is interesting and quite exciting actually about where we are today with engineering is we're at a time where there's so many new technologies coming about that I genuinely think can transform the way that, we do engineering design, scientific analysis. And the way that I guess we like to think of it at NVIDIA, and I think that's true also with our partners as well, is this sort of pillared approach. So let me go through maybe in the detail, and then I'll try and pick them apart. Good morning. I've got some of the people, the comments here, so I'm just trying to keep an eye on who's actually here. So some person say good morning, so good morning. It's obviously evening for me because I'm in the UK. So let's go through some of these. So the first one, I guess, is no surprise, right? It's how do we accelerate some of these codes? So if you're doing CFD analysis, so my background is computational fluid dynamics. That's how I started. I was and am an engineer. But I actually did it, in real life, trying to come up with cars and things like that. I worked in Formula One a little bit, although more as one of the CFD methodology geeks than the cool people designing the car. I never got to do that. But the first one is how do we make those codes faster? And that's for obvious reasons, so that you can get either the simulations you run today back sooner, for obvious reasons, make faster, you can do more designs, or do simulations that maybe you couldn't do before. And there is a difference to those two, but both of them are covered, I guess, by the first pillar. And we'll go into some of those details. The next one is AI physics. So AI surrogate models, ways of developing, training AI models that can enhance the efficiency of your simulation. This isn't a replacement for Pillar 1, but it is a really interesting area that probably many of you have started to look at, where you can get that real-time prediction, something that, even if you throw 100 GPUs at a problem, it's probably not going to become real-time. And that's where the AI comes in. The third one, and these sort of build on top of each other, I guess, in a way, is and hello, somebody's in Boston. Great. I love Boston. It's a very cool place. It's also the closest place to get to from the UK. So anything that has a short flight, I'm happy with. The third one is interactive digital twins. I think this has long been a dream that you could do a real-time changing, see multiple attributes in one digital twin. Now, there are different definitions. Some people have digital twins, so I can maybe explain how we see it. And that's using some of these AI surrogate models to do that real-time thing. And I've got a cool demo to show you a little bit later. And finally, the one that has been a bit of obsession of mine recently to look into is the whole agentic AI. Like, how can we build an AI engineer that, you as an engineer, and let's say I'm assuming you are an engineer listening to this, you can use that as your helper to automate and do things faster. So between those 4 areas, that's where that encompasses the focus that we have inside NVIDIA when it comes to industrial engineering. So maybe let's walk through that in a little bit more detail. And of course, if you've got any questions on what I've said so far, put it in the chat. We'll try and respond to it. So this is without AI, right? Let's just assume that we're going to do some design. So if it's a car, if it's a plane, it's a data center, if it's a device, if it's a semiconductor chip, you're going to do some design. And you want to simulate it. And then you want to look at the results, basically. So in between those steps, you do some pre-processing. So the design and the CAD, you might be using something like, CATIA, or you might be using Siemens NX or Autodesk. You draw the thing, and then you try and do the simulation. Simulation could be in a wide range of codes, and I'll talk in a moment about how we're helping to, accelerate them with GPUs, and then do some of the visualization, the rendering. And often you're doing this loop. Obviously, you want to try and optimize it. So where does the AI come into this? Well, first of all, the reason I say that pillar 1 is so important is because the simulations are making the data set that you're going to go and train on. And that is quite different than maybe the way that you might use LLMs today. Most likely you're using AI models that have been pre-trained and you're just doing an inference on them. Today, and things may change in the future, and that could be a separate topic about foundational models for CAE, etc., and more AI of the science. But today, you are actually going to go and train a model yourself. Today, you're going to go and take your simulation data, train it, and then you're going to come up with some AI physics models. Now, I'm going to show you a demo of why that is of particular interest and why that can lead to some real-time opportunities. But there's another interesting area, which is imagine if you want to try and put the AI model into your simulation. What if you wanted to still keep perhaps the benefit of your sort of physics-based conventional simulation with all the benefits that it has, but you want to somehow accelerate it? Well, there's some really interesting applications of that, and I'm going to switch in a minute to show you a couple of papers. For example, you could use AI to initialize the solution better. You could use AI to come up with a better mesh or numerical settings. Now, the final one, which is, I guess, the dream in a way, is how could you use AI to go around the whole loop? How could you use it to do the design optimization and ultimately use AI to generate perhaps a geometry or case that meets your needs? The point of this diagram, I guess, is to sort of show the possibilities of AI. And it's in every bit, and many of them are interconnected. And, one of the things that we have, and this actually started more than a decade ago, I think, I could be wrong exactly on the timing, is PhysicsNeMo. So PhysicsNeMo is an open source framework that really is designed that you as a developer, and I will make a distinction between a developer and an end customer in a way, which is the main focus is for a developer to be able to train models, build architectures, and take the cutting edge science and use it within, a design process. I say that because one of the things that is really, and this is a good slide to re-emphasize it, we love working with partners, startups, ISVs, developers. And so when I say go and use PhysicsNeMo, really we want a developer to take it, and then maybe you're going to put it in to your code that you go and take to an end customer. This PhysicsNeMo isn't really it isn't an end customer tool, it's a developer tool. And so we're really excited when we see ISVs and startups take PhysicsNeMo into their package that you can go and take. And I'll speak about that in a little bit in a moment. So one of the things I want this live stream to be is not just slides, right? Not just slogans. I want to get into some of the technical details. So for that reason, I'm going to jump out of this a sec, and I'm going to show you some of the really interesting research and papers that are backing up some of these claims. That's the one thing I think sets apart in some ways NVIDIA, is that we are a deeply technical company that want to move forward the community and contribute it through great science, great research. And so that's why I really want to, get into the details and show you some of the science and the reasons behind that. So what thing I'm going to do, is let's start with slightly higher level, which is a great blog that actually was written by some of my colleagues that really sets apart this like AI-powered CAE simulations. And I say this because you may be looking at this presentation and you go, okay, this sounds nice, but how do I actually do it? Well, this blog was written with that in mind, and it's basically full of links. So maybe if Boomi or someone can share this link in the chat or however it works on StreamYard, I'm not sure how to copy it in, then people can follow this because it's got a whole bunch of links of exactly how you can go and play around with PhysicsNeMo and see how this works. You can go and and what's really cool is we've got all the steps in the process. So literally how to take some of your simulation data, how to work it through the pipeline, how to train it, some details on the different architectures. And we're going to have a deep dive in this. I'm not going to try and go through all of it now, but we're going to have a session where we go through graph neural nets, transformers, neural operators, talk about the differences, the nuances, where the research is going. But if you follow this blog, you can go all the way through it and get to the point, and this is maybe a bit of a sneak preview of what I'm going to show you in a minute, is how you can then go and build a real-time digital twin on this. And one of the things you may be aware if you know NVIDIA, but if you don't, we have a thing called the Deep Learning Institute, which is basically a place where you can go and study and learn and do courses. And so if I make sure I don't bring up the wrong link, we have where is it here? Here we go. Accelerating Computer-Aided Engineering with NVIDIA AI Physics Technology. So this is basically a full course that goes through how you can do the data processing, the architecture, the deployment, everything, and get to the point we can do. So I would highly encourage you to look at this if you want to go from, just seeing cool stuff, but actually getting hands on keyboard and try yourself. And I'd love feedback. Did you like the course? Is there anything missing? Can we improve anything? Now, one of the things that we are also trying to do is really advance the state of the art. And I'm only going to tease these. So this is one paper, X mesh GraphNet. Well, it's not easy to say. And I'll just only briefly say the point is we were trying to address some of the issues with previous ML architectures, how to make them better, how to make them more scalable. And so we got hands in, was doing some of the science, and that science model is available in PhysicsNeMo. That's the same with this other one, this factorized implicit global convolution for automotive computational fluids prediction. Wow, what a name. Luckily, the next one's called Domino. That's easy to say. Again, we'll have a deep dive on this. But all of this is to say that when I say that we're working on the AI physics, that is a whole level. It's at the fundamental science. We have colleagues in NVIDIA research who are doing fantastic work as well. It's with the PhysicsNeMo team. And the whole point is to bring that then to our ISV startup partners, and hopefully they can then deliver it to you through the packages they use today. Okay. So that's, again, a bit of a teaser. Hopefully I haven't put you off by showing too many journal papers. I'm sure the people behind this live stream are freaking out going, why are you showing so many journal papers? But sorry, I am an academic by heart, so this is what I like to do. Okay, so let's maybe jump back to the presentation a little bit. Well, I guess summarizing it is this sort of thing, essentially, where we see that, traditionally maybe, and again, apologies for using CFD. I am a computational fluid dynamics. This is also relevant for CAE more broadly and EDA, but I'm just using it because CFD also makes pretty pictures. Is the wind tunnel, days, weeks, normal CAE simulation, maybe hours or days. If you can run it on the GPU, maybe you can speed it up by an order of magnitude, but it's the AI physics that really gives you the real-time ability. But, one of the things that we have is we are focusing on the first pillar. How do we accelerate the codes? We work with all of these different startups, ISVs, government codes, and we have some amazing people some of them are called dev techs. So these are the like real smart guys and girls who know how to optimize codes and work hand in hand with these companies to optimize and tune them for the latest NVIDIA GPUs. And so we see orders of magnitude speed up across the range, not just in CFD, in EDA, and in FEA. But one of the things that people do not realize is CUDA-X. I must admit, I came late to the party and appreciating some of this. And we've got quite a cool video that I'd like to show. I hope you've got some headphones in because there's a really nice soundtrack and talking. So I will let the video play, and it talks about CUDA-X, what it is, and how it's transforming things. So maybe, Mark, if you could play.
To the creators, the pioneers, the builders of the future, CUDA was made for you. Since 2006, 6 million developers in over 200 countries have used CUDA and transformed computing. With over 900 CUDA-X libraries and AI models, you're accelerating science, reshaping industries, and giving machines the power to see, learn, and reason. Now, NVIDIA Blackwell is 50,000 times faster than the first CUDA GPU. These orders of magnitude gains in speed and scale are closing the gap between simulation and real-time digital twins. For you, this is still just the beginning. We can't wait to see what you do next.
Yeah, for me, that video is such a cool. I actually have goosebumps. You can even see it on the camera here. Because the headphone, the music, and I actually should say, and I don't know whether I should say this or not, but there's some amazing people who work on those montages, some amazing technology, creative people that really brings it to life. The soundtrack that I seriously am always blown away, and it really helps to, show the work that our partners and customers are doing in this space, and hopefully to motivate you to see why it actually is changing how we can do things. So I love that video, and come to GTC, and you might see some more videos like that. There's GTC DC. I'm actually going myself in Washington DC, so you should come along if you're able to on that side of the world. Okay, so CUDA-X covers many areas, and what we mean by that is we're building these. In fact, let me skip to the next slide. Notice I haven't spoken about GPUs much. Of course, we have some amazing GPUs. These are massive. It's the rack. I think that if you go to GTC, there probably will be a GB200 on the show floor, and you can actually stand next to it and see it. It is incredible, the size, I think 1.5 ton. And the estimate, and this will depend a little bit on code to code, a GB200 NVL72, so with 72 GPUs, is equivalent to about 400,000 CPU cores. So in just one rack, you have the amount of compute that would have previously been in, like, I don't know, a top 50 supercomputer in the world. And of course, you can have hundreds of thousands or tens of thousands of these racks. So it's just incredible. But the reason we show the video about CUDA-X is because, we have amazing GPUs and the CPUs and the NVLink. And, we have amazing people in our hardware division who are focused on that. And that's because if you're running, let's say, CFD, you're not running just one GPU. You're running across many. And so the interconnect matters. The CPU matters. The rack level matters. NVLink was designed to help that, latency and bandwidth. But the bit on top, before you get to the ANSYS, before you get to the Cadence and Synopsys and Siemens and all the other great partners we have who are at the top of the stack, let's make it be clear, NVIDIA in industrial engineering is not building at the top of the stack. That is where we have our partners. But where we are helping is in the layer between. And we're building these libraries. And seriously, when I joined the company, I was so impressed. There's some amazing smart people who are working, though, on quite specific things. So what if you need a sparse solver? Well, we have a library for that. What if you need a multigrid method? What if you need to calculate, a fast Fourier transform? We have these, QFFT, QDSS, QBLAS. These are libraries that you can take without being an expert in CUDA, and actually is part of the way that we can deliver the speed up to the end code. So if you're a developer who is wanting to write their own GPU native code, I would definitely look first at whether you can use some of these libraries rather than do it from scratch. You could do it from scratch, but we've put so much time and effort into doing it. And every time a new GPU comes out, we've already worked on optimizing it because, of course, we've had access to it internally for a while. So that's why I talk about CUDA-X. And you can have a look on the website. If you type CUDA-X, there's hundreds of different libraries, and we'll have a deep dive on that. So we'll have a deep dive on the CUDA libraries and what are relevant for CAE and EDA, and we can talk about that a little bit more. But okay, I just wanted to, I promised this would be 20 to 25 minutes, and it's already at 22 minutes. So I probably should speed up a little bit here. And we can have a session on hardware. We can talk about the nuances. We can geek out on hardware, so we can definitely do a session on that as well. But what I wanted to do was show a few examples. This was a great slide for Fun3D, which showed the normalized speed up versus the bandwidth. And the point of this is that the bandwidth that you have going from A100 to H100 to GH200 to GB200 keeps going up and up, and you're able to realize that speed up. Whereas the speed up on the CPU curve is so much slower. So do you see why the generational jump, why moving, you want to be on the green line? Because as you can probably extrapolate where the green line's going next, the red line keeps being further and further and further away. And that's actually an interesting comment, that if you tested on like an A100, you really should test on a GB200, because whatever speed up you saw with the A100 versus your CPU code, you will see tremendous speed up by going to the newer generations. Now, the danger of me trying to show some partner slides is I'm probably haven't got all the partners, and someone's going to shout at me for not including some partner, and that's not intentional, but I did want to bring out this because I want to take a few as an example. This is with ANSYS. ANSYS is one of the biggest simulation companies around. Probably most people watching this will have some experience of using ANSYS Fluent or ANSYS Mechanical or Discovery, or many of the other tools. The speed up, so this is the driver case, which is quite a popular automotive or open source automotive. And this was running on TAC, the big system in the US, GH200. And the number that comes to mind is 29 days to 6 hours. Now, 2,000 cores is still quite a lot, and many people in engineering will still be running on 2,000 cores. But 29 days means that you'll never be able to do that simulation, or only on like an academic supercomputer. Whereas 6 hours on 320 GPUs. Okay, now let's me level with you. You're probably not going to run 320 GPUs for your simulation. I accept that. But even with, let's say, 160, that's 12 hours. Or maybe on 80, it's a day. It's still a massive speed up. And this is exactly what is motivating and transforming the ability to do bigger simulations. The fact that you can do it. And if I was to now throw the GB200 number on this, it would be faster even again. This was also another one. There's actually this was Siemens and BMW. I've tried to put a link in the bottom. Maybe we can, I don't think I passed this to our team, but there's a GTC presentation from this year where we actually went through where there was a talk exactly about this. So this one slide cannot, fully do it. But it was a great talk talking about the nuances, how the evolution had gone with the Siemens product. I think this was Siemens Star CCM, and how they'd gone from like 4 hours to 20 minutes and some of the nuances of the setup cases. So definitely want to call out. This other one was really cool. This was with Cadence. So this was some work that was done for aeroacoustics, for turbo machinery. So like 50 minutes on a B200 versus 70 hours on a CPU. So all of these is just to basically say that there is so much transformation now in doing, and for people who understand what I'm talking about on this, like when it comes to doing bigger simulations like wall-resolved LES, doing finer meshes, it's not just about running your simulation faster, it's about doing things you couldn't do before. Okay, changing track a little bit now, going back to maybe a little bit more the, oh, shoot, I forgot to show you the demo. Right, let me do that. Okay, I wanted to show you this, and you can see how disorganized I am. Okay, well, let me just reconnect this, hope this works. Okay, so one of the things that I was hoping to show you this, okay, I really hope this works. Yes, brilliant. So I spoke before about AI physics. I spoke before about digital twins. But it was sort of hard for people to visualize what it would be like. You know, we've got a developer toolkit like PhysicsNeMo. We've got Omniverse. And we wanted to give people an easier way of understanding the art of possible. We wanted to help ISVs and startups see the potential of this technology. So what we did was we created a blueprint, a reference architecture. It's not a product. It's just a reference architecture to show the art of the possible. And you can go to this website, and we can put the link in the chat. But basically what it does is it gives you the ability to do a real-time. So I'm going to pick a different car model now, and it's going to change and do an inference on that new car model and give the streamlines. Now in the back end, it's an ML model trained with thousands of CFD simulations in PhysicsNeMo. It's then trained the model. And now in this, I'm giving it a new geometry, and I'm doing an inference against that model, and it's running on a few GPUs on the back end, and it gives you the answer. But what's cool, this isn't a video, by the way, this is Omniverse actually running. You can do the real-time streaming. You can look at this. If you come to GTC DC, you'll see a cool show floor demo. I can't say what it's about, but it'll be cool. But what's even better is you can actually go and use this. You can go and test it yourself. If you go to this page, Digital Twins for Fluid Simulation, GitHub, we've put it completely here. You can actually deploy this. You can do it to see the art of the possible. But what's great, remember, the whole point of this was to show, thought leadership and to try and encourage. We had a recent announcement that ANSYS is now integrating Omniverse in their Fluids One package. So if you're a user of ANSYS, you're going to be able to go and have this sort of experience of having the Omniverse environment within the solver. So that was our main goal, is to show the art of the possible, push the boundaries, and then hope that you can use it in the tools that you have every day. So play around with that website thing. I think it's pretty cool. And it's great to see so many other companies now building this for themselves. Okay, I really should speed up. All right, I'm just looking if there's any. Great. Okay, I can see there's some good chat. I will jump in on LinkedIn or YouTube later and respond to some of these questions if I hadn't had a chance now. But what I wanted to do was just go maybe back down to the developer level a little bit and just briefly talk about Warp. Warp is a really cool framework. It's a Python domain-specific language for writing GPU-accelerated kernels. Now, there's many different use cases for Warp, actually, but there was a great blog done recently, which I'll jump to in a second, which was done to show how you could do it for a computational fluid dynamics of a city simulation. And I would say that Warp is the epitome of the modern day programming environment to write and get the best out of the NVIDIA GPUs. There's so much in there to make it easy. So it has that, you don't have to be an expert in CUDA. You can just write it, as you can see on the screen here. You can go and write a solver. And just to prove that point out, if I just jump, hopefully, to a blog that was done here. Is it? I was trying to find. There we go. So it was Autodesk Research brings warp speed to CFD. And it was basically work done for them to use Warp to accelerate this. And there's a whole blog describing how it's done, some of the differences to JAX, for example. And I would highly encourage you to go and look. There's a GitHub repository for it. There's a publication. If you are watching this as a developer who's wanting to write their own CAE code, whether you're an academic, please have a look at Warp. It could be something that would really help you to have an easier time doing it. Okay. Very nearly finished because I promised. I usually talk too much and write too much, and I promised this would be a short, snappy one. So I will finish it soon, I promise. This is like a bit of a summary. So Warp, CUDA-X. We didn't really talk about the NIMs. We can talk about the NIMs next time. PhysicsNeMo, Omniverse, they all come together. There's a cool thing on Omniverse here. This was the whole point of the digital twins. That's really, hopefully, a rush through, but it wasn't so much a rush. I think we did it in about half an hour, talking about some of the work that we're doing. I will stress it again at the end. What we really, our NVIDIA's strategy or vision or desire is to enable you as a developer, and whether you're a developer, an academic, at a government, a developer at a startup, a developer at an ISV, to help accelerate your program that you would go in and take. So that's why it's great. And I had that big list of ANSYS and Siemens and Cadence and Synopsys and Neuroconcept and PhysicsX. I'm probably going to miss out names, which is always dangerous when, you know, people get insulted. Hopefully I'm mentioning all the companies, you know, and like Dassault and others who we work so closely with. And it's great because hopefully then you can just go and, you know, double click and download their tool. But hopefully you enjoyed this. And what we're going to do is we will have a series now of deep dives. I think we're probably going to do the AI physics one first, which is going to go in to deep diving exactly on how some of these work, some of the ML architectures, some of what our partners have been doing in this space, some of the latest science, some of the latest research, how it applies for CFD, FEA, EDA. So please stick around. I encourage you to have a look at all the links that we put up during the course of this session. I will probably jump in to probably LinkedIn, so you can follow me, Neil Ashton, if you just search for me. I'll try and put any extra details and jump in and maybe answer some questions from here, unless there is some other one. No? Okay. Yeah. I'm going to stop there because we're going to run out of time. But please join next time. We'll if you follow the NVIDIA AI channel, the data center channel, if you come onto YouTube, onto X, and we will post it on there. But thank you for joining. I really had fun. I hope you learned something along the way, and you join us for what is going to be hopefully an interesting series of sessions. So yeah, go on Discord. I actually need to get an account on Discord. I don't even go on Discord. So I will join you on Discord if you do too. But with that, thanks very much for joining. And I hope you have a great Thursday, Friday, and weekend. So thank you.